inverse trig functions. So I first just want to remind you what an inverse function is. So basically, if you have some function f, then remember that this function accepts one number as an input and then produces a different number as an output. The inverse of this function is a different function, which we represent as f with a little -1 up here. That means the inverse of f. This function basically switches the inputs and the outputs. So whatever f does to an input here, the inverse function will undo the effects of the original function. That's kind of abstract, so let's just sort of take an example to make it concrete. Let's suppose that f of x is the function 2x. All right, so what that means is that this function simply doubles the input. Whatever you plug into this function multiplies the input by 2, right? So for example, f of 5 would be 10, right? Okay, great. So the inverse function, okay, which is denoted f with a little -1 up top, this thing must undo the effects of this one, right? Now, look at this notation. This equation here is telling you that f sends 5 to 10. Well, the inverse function must undo that process. It must undo the effects of the original function. So if I take 10 and plug it into the inverse function, then the inverse function is going to undo the effects of the original function. So if I take 10 and plug it into the inverse function, I would get what? Well, I would get sent back to 5, right? So big picture is, if the original function sends 5 to 10, then the inverse function will send 10 back to 5. Inputs and outputs get switched, okay? So that's a very brief review of inverses of functions. Let's talk about inverses of trig functions. So inverse trig functions. Now, the first thing that I want to say is I want to make a comment on the kinds of inputs and outputs that trig functions have. So the regular trig functions, the ones that we've been working with, that's sine, cosine, and tangent. These functions, what kinds of inputs do they have and what kinds of outputs do they have? They accept an angle, theta, as input, right? The thing that you plug into a trig function is always an angle, which we usually represent theta. And what do they produce as an output? They produce, well, depending upon the definition you're using, could be a ratio of sides, right? Like opposite over adjacent. Or if you're using the unit circle definitions of the trig functions, could be a ratio of x and y coordinates, like y over x is the output of the tangent function. Or, for the cosine function, it would be x over r, some kind of a ratio. So the regular trig functions accept an angle as an input, and they produce a ratio of sides or a ratio of coordinates as an output. Now, the inverse trig functions, okay, which are denoted sine with a little -1 up top, cosine with a little -1 up top, and tangent with a little -1 up top. These functions must reverse the inputs and outputs. So what kind of an object do the inverse trig functions accept as an input? Well, it must be the same as the output of the regular trig functions. Inputs and outputs get switched. So the acceptable input for an inverse trig function is, they accept a ratio of sides. Hey, come on in. So they accept a ratio of sides as input, and they produce an angle as output. So notice that that's switched around from the regular trig functions. Instead of accepting an angle, they produce an angle. Okay, so now that we've seen that the inputs and outputs of the inverse trig functions are switched around, and we have observed that the inverse trig functions produce angles, I want to do a little bit of an example because I need to talk about a pretty serious problem that exists with all of this inverse trig function stuff. So let's think about the cosine of pi over 4. Now that's just a regular cosine function. It's not the inverse cosine. So the cosine of pi over 4, what is it? Well, it's the x-coordinate associated with pi over 4 on the unit circle. If you look at the unit circle, you'll see that it's root 2 over 2. Cool. Now let's think about the cosine of 7 pi over 4. Again, that's the x-coordinate on the unit circle associated with 7 pi over 4. If you look at the unit circle, you'll see that that x-coordinate is, again, root 2 over 2. Great. Now what I want to do is I want to take the inverse cosine function. Okay, now the inverse cosine function, which is represented as cosine with a little minus 1 up above, that means inverse. It doesn't literally mean cosine to the negative 1. It means the inverse of cosine. I want to take the inverse cosine of root 2 over 2. Okay. Now, here's the thing. The cosine function, the original one, sends pi over 4 to root 2 over 2. And it also sends 7 pi over 4 to root 2 over 2. The inverse cosine function must send root 2 over 2 back to whence it came. Okay? The problem is, where did root 2 over 2 come from? Did it come from pi over 4, or did it come from 7 pi over 4? So really, it seems like there are two choices here. The inverse cosine of root 2 over 2 seems like it could be pi over 4, or it seems like it could be 7 pi over 4. And which one is it? Well, there's only one choice. Functions only have one output for every input. So just to summarize, the inverse cosine function has to undo the effects of the original function. The original cosine function sends pi over 4 to root 2 over 2. So maybe inverse cosine should send root 2 over 2 back to pi over 4. But the regular cosine function also sends 7 pi over 4 to root 2 over 2. So maybe the inverse cosine should send root 2 over 2 back to 7 pi over 4. Which angle should it send it back to? It's not clear. So this is a problem, okay? It's fundamentally a problem because multiple angles have a cosine of root 2 over 2. These are two of them. There are actually many more. This is a problem for inverse cosine, but it's also a problem for inverse sine. It's a problem for inverse tangent, and so on. So here's the solution to this problem. The solution is the following. We restrict the range of the inverse trig functions. So we restrict the range of the inverse sine function, the inverse cosine function, and the inverse tangent function. Okay, so here are the restrictions. The inverse sine function has a restricted range of negative pi over 2 to pi over 2. What that means is that the inverse sine function will only produce angles in this interval from negative pi over 2 to pi over 2. In degrees, that's negative 90 to 90. Okay? So the inverse sine function will always produce an angle within this interval, in radians, or if you're in degrees, that interval. The inverse cosine function will always produce angles in the interval 0 to pi, which in degrees is 0 to 180. And then finally, the inverse tangent function actually has the same restriction as the inverse sine function. It will always produce an angle between negative pi over 2 to pi over 2, or if you're in degrees, negative 90 to 90. Okay? And it turns out that these restrictions settle the question that I was mentioning here before. So, if we sort of go back to our question here, what is the inverse cosine of root 2 over 2? Is it pi over 4, or is it 7 pi over 4? Well, the answer is pi over 4. The reason why is, well, if you look at the restriction for inverse cosine must produce angles within this interval. Pi over 4 is in this interval. 7 pi over 4 is not. It's too big. 7 pi over 4 is bigger than pi, so it's just too big. It cannot produce that angle. All right, so let's do a few examples. Let's consider the inverse sine of, let's say, root 3 over 2. Okay? So whenever you see an inverse trig function, and this is an inverse trig function because of the -1 here, you should always remind yourself what kind of an answer this thing is going to produce. So what kind of an object is the inverse sine of root 3 over 2? This is an angle, right? Remember what I said. The inverse trig functions accept, coordinates or ratios of sides as an input, and they produce angles. So inverse sine of this thing has to be an angle. So whatever this thing is, and we're going to figure it out, whatever this thing is, it's some kind of an angle. Okay? Now, what kind of an angle, or what angle is it? What do we know about this angle? It's not just any angle. It is an angle whose sine is root 3 over 2, right? If you like, you can think of it this way. The original sine function will send our unknown angle theta to root 3 over 2, and our inverse sine function will send root 3 over 2 back to theta. Okay, so in other words, whatever this object is, it's an angle, and it's not just any angle. It is an angle whose sine is root 3 over 2. Now, one way of handling this is to say to yourself, okay, I'm looking for an angle whose sine is root 3 over 2. Now, if you go to your unit circle, here's a copy, you can go looking for an angle whose sine is root 3 over 2. Of course, the sine of an angle is just the y-coordinate of the associated point. So finding angles whose sine is root 3 over 2 just means finding angles whose y-coordinate is root 3 over 2. I see one of them right here. Pi over 3 is an angle whose sine is root 3 over 2. So perhaps our angle is pi over 3. Perhaps that's the answer. But that's not the only angle whose sine is root 3 over 2. On the unit circle, there's another one over here. Looks like 2 pi over 3. That is also an angle whose sine is root 3 over 2. So maybe it's 2 pi over 3. As a matter of fact, there are many other angles as well which have a y-coordinate of root 3 over 2. You could obtain them by adding and subtracting full rotations to either of these angles. But on the unit circle, we have at least 2 choices, right? Which of these choices is it? Well, remember the restriction for inverse sine. The restriction for inverse sine was negative pi over 2 to positive pi over 2. Which of these 2 angles sits within that interval? The answer is that one, pi over 3. 2 pi over 3 is just too big, okay? It's larger than pi over 2 because 2/3 is larger than a half. So this angle's too big. That's not it. It's actually this one, okay? Now, I sort of want to talk a little bit about a really tricky issue that always comes up with these restrictions, okay? Students, when they see these restrictions, they always sort of want to do the following thing. They say, negative pi over 2 to pi over 2, or if you like, negative 90 to 90. What does that look like on the unit circle? Well, of course, negative pi over 2 points straight down, and positive pi over 2 points straight up. And all the angles in between those would be this side of the unit circle. So what they sort of do is they say, oh, negative 90 to 90, that's just the right-hand side of the unit circle. It is true that the angles in this interval sit on the right-hand side of the unit circle. That's true. However, the right-hand side of the unit circle does not tell the entire story. Okay? You need to remember these intervals and not simply the right-hand side of the unit circle. The reason why is the following. The right-hand side of the unit circle
yes, could be represented by negative 90 to 90. But that's not the only representation. The right-hand side of the unit circle could also be represented by 270, which points straight down, all the way up to 450, which would point straight up. The restriction for inverse sine is this interval specifically, not merely the right-hand side of the unit circle, because the right-hand side of the unit circle could be represented by all kinds of intervals, all kinds of ranges of values, like this one here. But the restriction on inverse sine is this specific interval, not merely the right-hand side of the unit circle. Let's see why that matters. Okay, I'm going to do a problem that is kind of like the bane of students' existence when they study this material. They get it wrong so frequently, and it's really tricky. So I want to take a look at the inverse sine of negative 1/2. Okay? Now let's think carefully about what this is. This is an inverse trig function, and therefore the inverse sine of negative 1/2, what kind of an object is it? It's an angle. Okay? This is an angle. So whatever number this winds up being, whatever the answer winds up being, this is some kind of an angle. All right? That's what the inverse trig functions produce. But it's not just any angle. It is specifically an angle whose sine is what? It's an angle whose sine is negative 1/2. Okay, great. So we're looking for an angle whose sine is negative 1/2. Of course, the sine of an angle is just the y-coordinate of the point on the unit circle. So we can go to our unit circle, and we can say, all right, I'm looking for an angle whose y-coordinate, whose sine, is negative 1/2. Let's see, y-coordinate negative 1/2. Oh, there's one. 7 pi over 6. 7 pi over 6 has a y-coordinate of negative 1/2. Okay, so maybe 7 pi over 6 is the right answer. But that's not the only angle on the unit circle with a y-coordinate of negative 1/2. I also see 11 pi over 6 has a y-coordinate of negative 1/2. So maybe 11 pi over 6 is the right angle. Now, if you thought that the restriction on the range of inverse sine was simply the right-hand side of the unit circle, if you believed incorrectly that the right-hand side of the unit circle was the only thing you needed to think about in terms of the restriction, then you would say, which of these angles is on the right-hand side of the unit circle? Is it 7 pi over 6 or 11 pi over 6? Well, 7 pi over 6 is over here on the left-hand side. That's wrong. But 11 pi over 6 is on the right-hand side of the unit circle, so that must be the right answer. No, it isn't. It's wrong. Which of these angles, okay, so why is 11 pi over 6 wrong? Because it doesn't sit within the restriction on inverse sine. Look, the restriction on inverse sine is negative pi over 2 to pi over 2. 11 pi over 6 is too big. 11 pi over 6, I'm trying to fit it on the screen here. I guess I'll just write it here. 11 pi over 6 is too big. It's bigger than pi over 2, because 11 over 6 is bigger than 1/2. This angle doesn't sit in this interval. So which of these angles does sit within this interval? Neither of them. Neither of them are the right answer. Okay? We need to find an angle which is not just on the right side of the unit circle, but which actually sits within this range of values. Okay? And neither of these guys do the job. Now, it is true that the correct answer will lie on the right-hand side of the unit circle, but it has to be specifically within that interval of values. Now, I'll tell you something, I'll tell you sort of a secret. 11 pi over 6 is not the correct answer because it's too big, but it does sit in the right location on the unit circle. The correct answer, the correct value of inverse sine of negative 1/2, the correct answer does sit here at this location. Okay? 11 pi over 6 gives you the right location, but it's the wrong representation of this angle. We need an angle which sits here, but which actually lies between negative pi over 2 and positive pi over 2. The answer is negative pi over 6. That angle also sits here, which means that its sine is also negative 1/2. But not only does it sit in this location, it is literally within this interval, right? Negative pi over 6 is literally in between these two values. So therefore, the correct answer is negative pi over 6, okay? All right, so let's just do perhaps one more of these. Let's maybe do a tangent one, okay? So one more. Let's think about the inverse tangent of, let's say, negative 1. All right? And let's say I want my answer in degrees, okay, just for fun. Now, before you try to figure out what the answer is, you should think about what kind of object this is. What kind of a thing is it? Well, the inverse trig function, any inverse trig function, produces an angle. So this is the inverse tangent function of negative 1. This is an angle, okay? So we're looking for some kind of an angle. But of course, it's not just any angle. It's an angle whose tangent is what? Is negative 1. Okay? So we're looking for an angle whose tangent is negative 1. Now, I previously had you fill out tangent values on the entire unit circle. You can refer back to that. I have sort of a solution set right here. Here's the unit circle with all of the tangent values listed. Now, I'm looking for an angle whose tangent is negative 1. I certainly see 1 right here. That would be 135, so maybe the answer is 135. Okay, maybe 135 degrees. I also see this angle right here has a tangent of negative 1, so that's 315. Okay? Now, again, we have to remember what is, so, which of these is it? It's not both of them, okay? The inverse tangent function has a restricted range. It's the same restricted range as it is for inverse sine. In degrees, it's negative 90 to 90. Okay? Which of these angles sits inside of this interval? Neither of them. Neither of them does. They're both too big. Both of these angles are bigger than 90. Neither of them are right. Okay? If you think that negative 90 to 90 simply means the right-hand side of the unit circle, if you think that's all it means, then you're going to walk away and you're going to say, oh, 315, that's on the right side of the unit circle. The answer must be 315. That's wrong. 315 is not inside this interval. 315 is in the correct location, but it's the wrong representation, okay? The angle that we're looking for does sit right here. That's true, but 315 is the wrong representation of that angle. We need an angle which sits here, but does lie within the restricted range, negative 90 to 90. So what angle would do the job? The answer is negative 45. Do you see that negative 45 would land you in the same location, but negative 45 has the advantage of actually being within inside this interval? So the answer is neither of those. It's actually negative 45 degrees. Okay? So in summary, because this topic is tricky and it is weird and it is hard to understand, I just want to give you a little bit of a summary. The regular trig functions accept an angle as an input and they produce a ratio of sides or some ratio of coordinates as an output. Okay? So for example, sine of pi over 6 is equal to 1/2. So the input is an angle and the output is like the y coordinate, okay? The inverse trig functions accept a ratio of sides, or if you like a y coordinate, as input, so 1/2 is the input, and they produce an angle as an output, okay? But you have to be extremely careful, right? Because there are many angles whose sine is 1/2. And you have to choose the angle which lies within the restricted range for inverse sine, which of course is negative pi over 2 to pi over 2. It turns out that pi over 6, because it sits within this interval, inverse sine of 1/2 is indeed pi over 6. That's true, okay? But the behavior of these inverse trig functions is very strange because they sort of don't always send you back to where you came from. In truth, these functions are not true inverses. And I'll just kind of show you what I mean with a simple example. Sine of 3 pi over 4. If you evaluate that, you get root 2 over 2. Okay? Now, if I take the inverse sine of root 2 over 2, if this were a true inverse, then it would send this number back to 3 pi over 4. However, it can't do that because 3 pi over 4 is not within the restricted range. This is like 3/4 pi. That's bigger than 1/2 pi. Inverse sine can only produce angles within